Task scheduling. So the scheduling is a method by which task threads processes are allocated to computing resources. The task scheduling can also be defined as assigning a start time and an end time to a set of tasks. This scheduling can also be performed under time or resource constraints. So one of the considerations that is important to scheduling is load balance. And load balance tries to distribute the work uniformly across the computing resources. Let's look what happens into a parallel application. In the parallel application, you will have tasks. Those tasks will be distributed by the task scheduling algorithm over threads. And the threads themselves will be distributed to the cores. So the thread scheduling, for instance, if we look at the pthread scheduler, we have three parameters that drives it. First one is the scope, so that's the set of threads that are in competition. For instance, that can be at the process level, or that can be at the system level. You have to have a policy. So the policy, for instance, can be FIFO, first in, first out, or round robin. In that case, that means the time slice has distributed evenly over the threads to be scheduled. And third data for the scheduler is a priority of a task. So some tasks might be scheduled more frequently than the other ones. So the scheduler is mainly concerned with throughput, that is the number of tasks that is completed per unit of time, the latency, that is how long it does to finish a task, fairness, that is it distributing the computing resource uniformly across the task to be performed, and you can also have real-time constraints, that is you want to make sure that some task is performed by a deadline. This is frequent in embedded systems. You can distinguish two kinds of scheduling algorithms. The first one is a static one. In that case, the scheduling is performed before the execution, and it doesn't change during execution. You will use that, for instance, for in embedded systems where you have different computing resources that are fixed, and the algorithm, the task of the algorithm are also fixed during the execution, so you pre-allocate all the tasks over the computing resources. And the second class of scheduling algorithm is dynamic. In this case, this is performed at runtime, so you have queues that keep the task to be scheduled, and the allocation of the task over the resources is performed at runtime. Let's look at an example of work stealing algorithm that is frequently used in parallel computing. In that case, you have queues of tasks, and at the beginning of the algorithm, each queues receive a set of tasks to be performed. But at some point, some cores here may become idle because it doesn't have any more tasks to execute. So the idea, it looks what are in the queues of the other cores and steal part of the work that was allocated to a busy core, so it gets some work done by itself. One of the ideas behind that is you minimize the thread migration. That is, you migrate a task or a thread only when you have no work to do. Otherwise, you use the tasks that were allocated to you initially. This strategy is used in TBB, Silk, and other thread package for parallel computing. Set of questions. Why do you want the scheduler to allocate a task always on the same core? What are the two antagonistic objectives for the scheduler? What are the conditions to make migration of a task on a different core beneficial? So when should I move a task on a different core? And what are the disadvantages of centralized versus distributed scheduler implementations? If you have a lot of cores, a lot of threads, one scheduler might not be might be a bottleneck for the application, so you might want to use a distributed implementation of the scheduler, but there is a price for that. So what is this price? This is what this question is asking. And two references. So see you in class.